Hello, my name is Ying. Today, I'm going to introduce you our new piece of work, determine construction method patterns to automate and optimize scheduling using a graph-based approach. When we say construction method patterns in this paper, we mean a series of construction sequences that has been frequently used in the project. We will further explain this concept and why it's important in the later slides. Now, before we get to start today's topic, let's have a look at a very nice picture. This is Sydney Opera House, which is an iconic landmark. But local people also know this project for two reasons. First, this project was delayed for 10 years. And second, this project was over budget for more than 1,400%. Well, unfortunately, this phenomena is not unique in one single country. It exists across different countries and especially in large infrastructure construction projects. Of course, there are many reasons to cause this phenomena. For example, the political factors, the policy changes, natural disasters. But what we can do as researchers and construction companies is trying to produce a more accurate and quality construction plan to minimize the risk of being delayed as well as the impact of delay. But from the childhood, we know how important, we know that we can learn, human beings especially, can learn from the failure, and we can summarize why we failed and avoid to make the same mistake. Well, similarly, we can do the same thing to improve our schedule quality. So we can look at the the project schedules of previous projects and find out what are the reasons for running delay, trying to avoid making the same mistakes. This is also the whole purpose of this paper. This figure that you're showing at this moment highlights the difficulties to solve these problems that we just mentioned earlier. We all know that at this age, we have lots of access to data, like big data and everything. And machine learning outperforms human brains in terms of processing the data more effectively. However, can machine learning more specifically always process the construction schedule more accurately and more precisely than human brains? The answer is no, unfortunately. This motivating case, the slide that you're seeing at this moment, explains why it can't. This is a screenshot taken from a foundation construction project happening in the real world from our contractors. There are two levels of breakdown structure. The top one is base construction. For example, base 3, base 4, and probably base 5. That is written in the black bar on the blue ribbon. And then the green bars that you're seeing are the construction activities to deliver the base construction. For example, excavate, formation, and followed by concrete, strip and cure, and then backfill. From the first look, okay, nearly all these base constructions are similar, especially base 3 and base 4, which are literally identical. However, if we compare base 3 and base 5, which is the last one, it's a slight difference. We can see that these two activities, blind and reinforcement, were not shown or illustrated explicitly in base 3. But if schedulers and project managers can still understand what they should do, even though it hasn't been written explicitly. So that is the problem of the existing scheduling practice to machine learning, is that there exists many inexplicit information that has been hide from the readers or the machines, because human brains can understand and analyze such inexplicit information by referring to the overall context, but machine at this moment cannot do that. So to solve this problem, we propose a graph-based method, or we call it GCM method, to identify the common patterns or the frequently used construction sequences across different projects in order to automate and optimize the scheduling for new projects. Well, the proposed method first starts with data pre-processing, and then we prepare two matrices. One is feature matrix, and another one is adjacency matrix. We will further explain what does each matrix mean later. And after we got two matrices, we form a graph convolution network that can classify different activities into labels, especially our predefined labels such as wall, slab, foundation, and etc. And then we connect all those activities under the same label together into a sequence, count the frequencies of these sequences to tell whether it is a frequently seen construction sequences. So back to the matrices. So we mentioned feature matrix. In graph theory, feature matrix is the representation of the features of each node. In this case, each node is a construction activity, and the feature matrix is the numerical representation of the construction activities, including its text descriptions and durations. While the adjacency matrix is much easier, it shows how each activity is connected with others. We will see an example in the next slide. For example, in this sample project, we have 4 activities, A2, B2, and C2, and they're connected in different logics. For example, finish to start and start to start. This one is the feature matrix, because we mentioned earlier that the feature matrix is the feature representation of each node, including its text description and duration. So the size of the feature matrix depends on the number of activities we have in the project, and also the word embedding size that we have. Well, the word embedding we got in this study is we trained a fast text model to represent the text description in numerical words, in numerical numbers. And then this is the adjacency matrix. So in adjacency matrix, we have this pre-assumption that each activity has a self-loop with itself. So we can see there's the diagonal values is always 1. But the off-diagonal values shows how this activity is connected with another one. In this case, in this study, we didn't use 1 to represent it is connected or not. We incorporated the the logic link between activities, for example, finish to start or start to start. We use a relative percentage, see how much percent this logic link specifically has shown in this project. For example, the finish to start has showed 3 out of 4 times in these sample projects, whereas the start to start logic link has only shown once. So therefore, this the value between C2 and D2 is 0.25. And then eventually, if we feed these matrices together into a convolutional network and get it to trained, we will classify out whether which label each activity is going to. For example, activity A2, B2, and C2 may belong to wall construction activities, whereas D2 may go to slab construction activities. In this case, we connect A2 and B2, C2 together because they are under the same category, under the same label. And now we will form a link, a sequence for these 3 activities. So overall, we collected over 5,000 project schedules from a tier 1 contractor in the UK. And the features that are included in the data are the work breakdown structure, the text description, duration, early start, and early finish of construction activities. So even though that we had over 5,000 projects, we only used these 5,000 projects to train our language model that is getting our word embedding, because in this case, the word embedding can cover as much words as possible to cover the variety of the words in different types of projects. But eventually, for the GCN training, we only used 27 labeled projects because of limited manual effort to label these project activities. Among these 27 projects, most of them are laboratory and facilities, and then followed by nuclear power station and wastewater treatment plant. In the GCN model tuning, we have 2 hyperparameters in this study. The first one is the number of neurons in the hidden layer, and the second one is the learning rate. Eventually, we found that the model with 60 neurons in the hidden layer at a learning rate of 0.02 showed the best performance in terms of the loss and F1 accuracy. And the result, we found only, unfortunately, 1 method patterns that has been shown frequently across 2 projects. For example, that is the one that you're seeing at this moment, excavation and backfill sequence. This sequence takes about 0.6% of the total project time in one of the projects it has shown, and another one takes about 1.3%. Even though the result is very promising, we still have some problems existing in this study. That is the difficulty to distinguish 2 similar activities. For example, the second activity you can see in this sequence you're seeing at this moment, piling to autoclave maintenance level and AC base 185 versus the activity connected to it, piling to AD bases 32. These 2 activities are both piling activities, and they are nearly exactly identical except the project location constraint. So we found it a bit difficult to eliminate one activity from another one, because we tried to compare the cosine similarity between these 2 activities, as you are seeing in this table. Cosine similarity is a statistical metric to measure how similar 2 documents are. It ranges from -1 to 1, and 1 indicates these two documents are exactly the same. So unfortunately, these two activities that we just mentioned has a cosine similarity about nearly 0.99. So it made it a bit difficult to eliminate one of the activity from the sequence using the statistical values. So that's the challenge still remains, and we hope to resolve this challenge in the coming future research. Overall, our research in this paper unpacked the construction schedules into sequences and configure the frequently used and the most time-efficient construction sequence process for different building elements, for example, foundation. And the results help to generalize the construction schedules to help the industry professions to start a new project planning more effectively. Thank you.